indicators, the moments, I mean, of inertia of the rotational motion of the solid bodies. Indicators of inertia of the rotational motion of the solid bodies, article 10.4 of the book Mechanical Systems, calculations of the marine facilities. A little bit about the theory. The polar moment of inertia of mass of the mechanical system of rigidly connected elements at points mk relative to the point 0, the reference point of the Cartesian coordinate system, is equal. The polar moment inertia equal to the total, if we have the discrete mechanical system consisting of the separate points, separate concentrated loads, for example, and the total of the masses of the loads multiplied by the squared radius from the reference point to the definite one point k squared. This is a polar moment of the inertia. If we have the continuous body, not the discrete one, but the continuous body, so the polar moment of inertia equals integral by the all the volume of the body could be this, like this volume shown on the figure, 10 for 1 squared radius multiplied by the density, mass density of the body. If I assume the even distribution of the density of the body, multiplied by the increment of the volume, the integral by the volume. This is characteristic of inertia. The finding of the characteristic of inertia very important in the dynamics. In the issues corresponded with the motion, with the accelerations, especially with the angular accelerations like the rotational motion, so the mechanical systems, mechanical bodies, or in the issues with oscillative, with angular oscillation of the bodies in mechanics to find the moments acting in the moments of the inertial nature, etc. One more index, the radius of inertia, rho y, is just the characteristic of the square root of the moment of inertia divided by the mass square root. So the dimension of the moment of inertia of the mechanical body is the units of mass multiplied by squared unit of the size. As well, if we do this for the continuous body, radius of inertia is the square root that is there is in the units of the size, units in the international system is meters here. So we can, if we define this moment of inertia as rho y, this rho y have to be 2, but this rho y, the polar moment inertia will be I equal to rho y, we can indicate here rho y, rho I, yes, squared, multiplied by m, mass of the mechanical system. Moment of inertia of mass of the mechanical system of rigidly connected elements relative to the definite axis. So we did told about the polar moment inertia relative to definite one point, considering the radius of the location of definite point around this reference point. If we are talking about the moments of inertia relative to the axis in Cartesian coordinate system, axis or abscissa or coordinate or maybe applicata axis, the moment of inertia of the mass is mechanical system of rigidly connected elements related to the axis. That is the actual moment of inertia is I L indicated here it was 0, that is polar moment of inertia relative to the reference point 0. This is a polar moment of inertia. But if relative to the axis, we indicate with the L. L is the indication of definite one axis. And the moment of inertia equal to, for the discrete mechanical body, as a total of the masses producted by the squared the distance between the axis and the point of the location of the concentrated load in the discrete system, hk squared. So this is hk relative to the axis z. This is this one is hk, but it's very long. Look here on the figure. Hk relative to the axis x abscissa, and this is hk relative to the axis y. This all shown there, like the arms, HKs, HKZ, HKY, HKX, this one very long here on the figure. They all are there perpendicular to definite one axis. So the shortest way between the point M of the mass M and this definite one axis. Okay, So as well, we can do that for the continuous body as an integral of the squared size. The size. I mean that the length from the definite one axis could be abscissa ordinata or applied axis squared to the segment, the very small segment, like the increment of the volume multiplied by the density, the segment of the mass considered. Moments of the inertia for the rotation motion or for the angular oscillation motions in the dynamics, the moments of inertia are characteristics of the distribution of the material within the mechanical body. That is very important for the decision of the issues of the mechanics, of the dynamics of the rotation of the mechanical bodies, or of the angular oscillations of the mechanical body within the differential equations. Let's keep considering that what could be the moments of inertia related to the axis if we consider the definite one extent from the each one axis. For example, this is very comfortable to see that is the extent from the axis z to the point mk. This is the shortest way. So we can define that as the square root of the squared this distance as the square root of yk and the xk, because this the stroke line is the same line as we have here, hkz, the same line. So this line length is square root of the square two legs. This xk and yk is like the diagonal of the rectangular, or just the hypotenuse of the right angle triangle here. But we no need, when we finding the magnitudes of the moments of inertia, we no need the sizes, the distances from the axis of rotation themselves, but we need the squared sizes. Squared size, we don't need to take a square root of the total of two squared yk and xk, finding the hk relative the z-axis. So we just can consider the squared magnitudes. So it is all enough, because that's what we need. We need to find the distance squared, not the distance as a square root of two squares in accordance with the Pythagorean theorem. But we need to have that as just a squared result of this size. So the moment of inertia or the rotation of the discrete body around the axis is equal to the total of the masses multiplied for each masses of the brackets squared. The coordinates of this mass yk and zk. This is due to the relative the x-axis. So we have here y and z. If we consider the moment of inertia relative to ordinate axis y, then we have used z and k, e and x. So in the brackets we do not have this indication, because we consider the rotation relative this definite one axis y. But the formula are generally the same. And the last one, the moment of inertia of rotation of the body, consisting of discrete parts relative to the applied axis, we can find this by the same one formula. But if we consider the z-axis, so in the brackets we do not have the z, we have only abscissa x and ordinata y coordinates squared, because we need to multiply these masses on the squared distance from the axis to the definite one location of the concentrated mass mk. The actual moments of inertia of the mass of a solid body by the integration over the volume, we can do it as well if we have the continuous body. This the last one factor in the integrand here, in all integrands, for the moments of inertia relative abscissa axis, relative ordinate axis, and relative the applied axis. The last two factors in each integrand is the increment of the mass. A very small increment of the volume, and we assume that we associate this density with this volume. So this is the increment of the mass, and this we can consider as the product of the coordinate of ordinata and applicata of the definite ones, increment of the mass. This is squared, as well as we had here for the discrete state. If we have the moment inertia with related to the x-axis here, x here, so we now need to have here in the brackets the x. Here will be the y and the z, the same as for others. For the moment inertia relative to ordinate axis, in the brackets we have to use the applicata and abscissas. squared total, and for the moment of inertia relative to the applied axis in the brackets under the integrand we have in the brackets the total of 2 squared abscissa and ordinata squared, but not applicata due to the axis. Here we have indication of the what relative to we find in the moment of the inertia. The polar moment of inertia as well we have here, because this is a total of 3 summands squared. This is for the spatial case as for the space, for 3-dimensional space in Cartesian coordinate system. This is analog of the Pythagorean theorem for the flat state. And this is a squared size of the diagonal of the right angle, the parallelogram. No parallelogram, but right angle parallelepiped. Diagonal, right angle parallelepiped, diagonal like RK is total squared yk, xk, and the zk. So next we can find the diagonal of the right angle parallelogram. Okay, and we have the polar moment inertia. The same we have for the polar moment inertia in the case of the continuous body. This is for discrete one, the total of the elements of the mechanical body masses. This is the integration by the volume of the body, by the volume of the body. And if we consider this equation, for example, this equation with these 3 equations, so we can find the total of these 3 equations. Total the moments of inertia, the magnitude set. This is scalar magnitude. The moments of inertia are scalar magnitudes. So we can find the total scalar magnitude, just a formal approach. This is total scalar magnitudes. And considering the equations into the brackets in which we can find, in considering here the equations into the brackets, we can find that the total of 3 moments of inertia relative to the axis, abscissa, ordinata, and applicata equal to 2 polar moment of inertia relative to the reference point of the Cartesian coordinate system. The relative. We can do the same as well for the continuous distribution of the mass, but it's not so much important. But this is just understandable. By the same logic, we can find that it not depend on the definite one case. Is it a continuous body? Oh, this is a discrete body. Finding of the moment of the inertia. In any case, 2 moments of the polar moment inertia relative to the reference point of the Cartesian coordinate system equal to total of 3 moments of inertia relative each of 3 axes of Cartesian coordinate system. Okay, next definite samples of finding of the moments of inertia for the characteristic body. The first body is the rod shown on the figure 10 for 2a. This is a rod distributed with axis x, abscissa y is axis of ordinate and z applicata axis. Let's consider the definite segment of this rod, a very small segment with the length of the decrement. Increment of this rod size of the length, and it is of even distributed density and the transverse section area. That's why we have this is thin rod, which is difference of the rod to the, for example, to the parallelepiped. The difference of the rod to the parallelepiped is that the one size of this rod is much greater than 2 other sizes. The size of the rod relative to the abscissa axis, L equal the size, is much less than the sizes of the rod relative to the ordinata and applicata axis. The same as here for the next example for the plate. This is a plate. Which is a plate? Plate is a right-angled parallelepiped, but the thickness of this parallelepiped is much less than the sizes of its lengths and widths. So this is what is the definition, the formal definitions of the rod and the parallelepiped. So let's consider for the rod here with the transverse section A and the very small increment of the length dx. So what is the increment of mass equal to density multiplied by transverse section area multiplied by the increment of the length. The rod mass equals to, and if you have an even distribution by the length of the density on the transverse section area, we will have that the rod mass equal to product of the rho is density by the transverse section area and by the length of the rod. And we have to find the moment of inertia of the rod relative to the axis y ordinata and z applicata axis, this one, y and z axis. It's important that the reference point coincides with one of the ends of the rod, not in the middle, but one of the ends. This is location of the reference point. And y and z passing perpendicular to axis of the rod through the one of the ends and polar moment of inertia, we have to find as well relative to one of the ends of the homogeneous rod. So the abscissa axis passes along the rod, and the perpendicular are two axes, ordinata and applicata axis. Okay, so yeah, this is the general definition. What is the moment of inertia of the rod? In this definite one case, three moments of inertia are equal to the same because we have only one dimension of the rod. We don't have second dimension along the ordinate and applicate axis, only the dimension, the size of the rod. We have only along the abscissa axis. This is integral by all the mass of the rod is increment of mass, and this is squared distance between the reference point and the point of location of the increment of the length of the rod. After mathematical transform, we can find that we can redefine the integral by the mass to the integral of the length in the limits of from 0 to L, the length by the length of the rods. And then after the substitute of all variables, we find the integral of x squared. What is this? Is x in the power to 3, x power 3 divided by 3. This integral of x squared by dx. And when I substitute the limits of the integration, first L next minus the same equation of the integral. We now substitute 0 in the subtractant. We can find that these moments of inertia, each of all three of the axis moment of inertia relative to axis y, z, and relative to the reference point 0, the polar moment of inertia equals, they all are equal, multiplied by L squared, the length of the rod, divided by 3. And the moment of inertia, due to the assume that the sizes of rod in the transverse directions along the ordinata and applicata axis are incomparably smaller than each length. We can neglect the moment of inertia relative to the abscissa axis. That is, we assume equal to 0 because the rod is of the very small sizes relative to the transverse direction of the x. This is characteristics of this all dimension moments of the inertia relative to two axes, ordinate and applicata, and the polar moment of inertia are characteristics of the material even distribution of the rod within each length. Okay, next let's consider the rectangular plate. Plate is a right-angled parallelogram, but was very thin because its thickness is much smaller than the sizes of the base of the parallelogram, of the parallelepiped. I'm sorry about that. It's almost a parallelepiped, we can say, with a definite distribution of the mass by the area of the parallelepiped. We have even distribution of the mass. Moments of inertia of the mass of rectangular plate having dimensions h and l. We have h and l. We have axis as well, abscissa axis, ordinate axis, and applicate axis, and we just allocate by these lines of the segment of the length along the h and the width along the l. We allocate by these lines, and in the intersection of this allocation, we can find this definite one segment of the mass with distance from the reference point indicated here by the stroke line from the allocated segment of the mass and the reference point of the Cartesian coordinate system. So one can find relative to the coordinate axis x, y, and z, two of which x and y pass along the sides of the plate by the integrating. We assume that these two axes, x and z, are go by the sides of the plate, and next one axis is perpendicular. And the moment of inertia relative to the abscissa axis is equal to mh squared divided by 3. This is about the same formula as we had here for the rod. And the moment of inertia relative to ordinate axis is ml squared divided by 3. So the inertia when we rotate relative to the x-axis relative to this the distribution by the x-axis of the material is not important for finding the inertial characteristic when rotated around the x-axis or around the y-axis. So is it like here if we would have the this definite one rod, for example, extended along the ordinate axis or extended along the applied axis, but it will no impact for the moments of the rotation of the moments of the inertia when rotating this. If we would assume the extension of this rod, this will not impact on the moments of inertia relative to ordinate and applied axis. The same as here. We have the same formula is useful for the rod. We can have the same formula useful for the moments of inertia relative to the abscissa and ordinate axis. And the polar moment of inertia I0, the no polar, this is a moment of inertia relative to the applied axis, is we have double integration by the length h and by the width along the abscissa axis. It's not so much important what is length, what is width, but anyway, this is limits of the integration. And the integrand, we have the brackets and the squared total of two squared sizes of x location of this definite one segment allocated here by these lines, and this segment the y and the x we have here the sizes between the reference point and this definite one point, and this diagonal of the right angle triangle of this hypotenuse of right angle triangle with the legs x and y. This diagonal we can find as a total, the square of this diagonal size, the magnitude, we can find as a total of two squared magnitudes of the coordinates of this definite one located segment of the mass. The segment of the mass is rho density. We assume the even distribution by the area of this plate by dx, dy, etc. The way we do find this integral, it's not so much important to consider here how to find this usual approach. First find the internal and then external. We can find that this moment inertia relative to z-axis equal to the mass multiplied by the squared sizes of this plate along the abscissa axis and along the ordinate axis h squared total, and divided by 3 is very close to the formula of the moment of inertia for the rod. Okay, and next let's consider the solid homogeneous disk shown on the figure 10.4.3. 10.4.3, this is a disk, solid homogeneous disk. We have abscissa axis perpendicular to the plane in which we locate the considered disk. This is disk in the plane. This even distributed mass within the disk. We have two axes as well, ordinate and applied axis. We can allocate very small ring in the disk ring by the weights dr and the distance from the center of the location of the center of symmetry, and exactly the same is as location of the point of the center of the mass of the disk. We have the variable r, it's variable r, and this disk is of uniform thickness as an elementary mass, and it is relevant to determine the mass of selected ring with weights dr by, like this mass is dr as a density rho multiplied by delta thickness of the disk and multiplied by 2 by pi by r. Is 2 pi r is the length of the circle, perimeter, and multiplied by dr is the thickness of the disk. And the moment of inertia of the mass of homogeneous disks relative to the abscissa axis, this one abscissa axis relative to the coordinate axis x, and the polar moment of inertia r. So this is general formula. The squared radius from the reference point to the definite one disk. All points are at the same distance from the reference point. All points located in the allocated ring. And after the mathematical transforms, we define the mass by the mass as the increment of the volume of the small size disk with the weights dr, and the perimeter definite 2 pr, and the thickness. So when we have the product of the thickness of the disk by its perimeter and by the thickness, the width of the ring by the thickness of the disk and the perimeter of this ring, we can have after the mathematical transform that the moments of inertia relative to the abscissa axis and the polar moment of inertia as well for the disk equals, they are equal mr squared r the external diameter of the disk, radius, external radius of this r uppercase letter, squared divided by 2. And the mass of the disk is pr squared multiplied by delta, but excuse me, this just only the lost, the rho have to be here as well, the density of the disk have to be here as well. So rho multiplied by pi by r squared by delta. The moments of inertia of the mass of homogeneous disk relative the ordinate and applicate axis are equal due to the symmetry, central symmetry of the disk. So the moment of inertia relative the ordinate axis equals to the moment of inertia relative the applicate axis, and they are m multiplied by r squared divided by 4. Oh, okay, so but I will not go so is a standard formula, and how to find it by the integration just enough to indicate how we find the first one, and the second one is by the same way is a formula available in the directores of the moments for inertia relative to the axis, which is in the plane of the locations definite one disk. The moment of inertia and relative to the axis perpendicular to the plane of the location of the disk, and the polar moment of inertia we did find here. The moment of inertia of mass of a round thin ring. So this is a round thin ring. What is the moment of inertia? We have abscissa axis, ordinate axis, applicate axis, and the radius of this ring. And relative to mutually perpendicular coordinate axis x, y, and z, the moments of inertia are. What the logic is? We can take the moment of inertia for the disk finding formulas, and we just can find this moment of inertia of the ring when we having this as the initial one, and considering a very small thing of the disk as the ring is the difference between the outer disk and the inner one. So this is not a big deal to consider this logic, but actually having the formula for the even distributed mass of the disk, finding moments of the inertia relative to axis and relative to the reference point in the Cartesian coordinate system, we can as well by the same logic find that the moment of inertia of the thin ring and the polar moment inertia of this ring relative to the reference point, they two are equal each m multiplied by r squared. And this is the moments of the inertia relative to the ordinate and applicate axis as well. So we can see that having the mass of this ring, so formally the moments of inertia are twice more than the moments of inertia for the disk. So for the disk we have the ix and I0 m r multiplied r squared divided by 2, and here we have just m multiplied with r squared. This is more inertial shape of the geometric figure because the mass concentrated by the perimeter, not by the whole circle, but just on the perimeter of the circle. The same, the moments of inertia relative to the ordinate and applicate axis are twice bigger than the moment of inertia. The same for heaven we got here for the disk. Okay, what next we have? Oh, okay. Moments of inertia of mass of the cylinder of the polar moment of inertia are. This is a cylinder here. This is a moment of inertia of the cylinder. We have three axes: abscissa, ordinate axis, and the applicate axis z. Cylinder of the radius r, and we have as well the next one axis coincided in the middle by the length, in the middle of the length of the cylinder. L divided by 2 and divided by 2, this is two sizes cylinder of the length L. So moments of inertia relative the center of the mass of this cylinder is m multiplied by r square divided by 2. Oh, just a moment, please. Oh, yeah. This is relative to the same as the disk. If you consider the moment of inertia relative to the applicata axis, because the cylinder is like the solid disk, but not thin, but a thick solid disk, and thickness is the length of this cylinder. So we have the same formula as we had previously. Here's for the disk here. The same formula, but the same as. But if we assume that the disk is very thin and not thick. Excuse me, very thick of the mass distributed by the length of by the heat. Okay, and then we can find that the moment if we do that for the location for finding the moment of inertia of relative to abscissa and ordinata axis. Yeah, but for the reference point associated with the center of the mass of the disk, there will be mass of disk multiplied by L squared divided by 12. And it's important what is the reference point, because when the reference point is the base of the disk, the point in the base of the disk, the point on the axis of symmetry of disk, on its base, at the moments of inertia will be related to the abscissa and ordinata axis equals to ml squared divided by 3. So is definite one case. Actually, we can find this moment of inertia relative to the base as assuming the own moment of inertia of the, it's not disk but cylinder, I'm sorry about that. Of own moment of inertia of this, this is own moment of inertia of the cylinder. And this consists of two summands, the own moment of inertia and the transfer moment of inertia. Transfer moment of inertia, if we consider the disk, the inertia relative to 0 point, but not relative to the center of the mass. The own moment inertia is if we consider reference point coincides with the center of the mass of the mechanical body. That then we can find the own moments of the inertia. If we consider the inertia when the mechanical body rotates around the axis outside the center of the mass of the body, then we can assume we have to account as well the own moment of inertia and the transfer moment of inertia for the extension, definite extension of the center of mass of the mechanical body relative to the reference coordinate system. If we do that not in the center of the, if we don't associate the reference point with the center of the mass of the mechanical system, of the mechanical body, sorry. With respect to the mutually perpendicular coordinate axis, x, y, and z, which axis symmetry of solid round ball? Let's consider the solid round ball not shown on the figure. 10, 4, 4, and the axis abscissa ordinata applicata Cartesian system have the reference point 0 in the center of this solid round ball. Which moment of the inertia of the solid round ball relative to abscissa ordinata and applicata axis is 2 divided by 5 multiplied by the mass of the round ball multiplied by the squared radius or the external radius of this round ball, and the polar moment of inertia is 3 divided by 5 multiplied by the same mass and the radius of the ball. And the ball mass is determined the well-known formula as rho multiplied by 4 divided by 3 by pi by r power to 3. This is a known formula finding the mass of the ball, considering the distribution of the mass even within the ball, the space, within the ball space. Okay, the theorem of the Huygens, Steiner, moment of inertia of the mass of the mechanical system of rigidly coupled elements of the moment of inertia, or moment of the inertia of the solid body relative to any axis is equal to the sum of the own moment of the inertia. We denote like I, C, Z, for example, yeah, of mechanical system. This means relative to the axis Z in definite one case. Relative to parallel axis passing through the center of the mass. And the transferring moment of inertia E0, if it not coincides a reference point with the center of the mass of the mechanical body, but any other arbitrary point could be arbitrary assigned, could be by the other causes assigned. 0 point of the reference relative to z-axis. This transferring moment of inertia is the mass of the mechanical body multiplied by d. D is the distance. This is distance between the point of this is C as the center of the mass of this definite mechanical body, and D is distance between the arbitrary taken system center of the reference and the center of the mechanical body C. Product of the mass by the square d by the square distance d squared between the axes. So we have the factor, the second factor in the transfer moment of inertia. The second sum at the transfer moment of inertia. So this is a moment of inertia relative to the definite one arbitrary taken the reference point of the Cartesian coordinate system with the axis parallel to the axis of the first one coordinate system associated with the center of the mass of this mechanical body. And we have the distance d, and the dm multiplied by d squared is the transfer moment of inertia. So we have the on moment of inertia and the transfer moment of inertia. And the theorem of Huygens Steiner means that the total moment of inertia relative to the arbitrary axis is equal to the total of the on moment of inertia and the transfer moment of the inertia of the mechanical body. Let's consider the exercise shown on the figure 10 for 5b here. We have the mechanical system consisting of the disc, it looks like pendulum maybe, that with a hinge and the disc. They have the rod 1 and the disc 2. And we have the axis abscissa and ordinata. This is a flat state, so we do not important for us the third axis z. We have only x and y, and this pendulum oscillates in the plate of this definite one draw. This oscillates, and the characteristic of inertia of the pendulum is important to find its element of the motion of the pendulum in particular when it oscillates in the flight state relative to the reference point 0. The mechanical system of the pendulum consists of thin homogeneous rod 1 of mass m and the length L, and the homogeneous disc 2 of mass m and the radius equal to 1/4 part of the length of this definite one pendulum of the force of the rod. The sum of on transferring moment of inertia for the rod is on and transferring moment of inertia is the on moment of inertia of the rod. We got this formula for the rod as mass multiplied by the length of the rod square divided by 3. The sum of the on and because we had originally the formula relative node, when we got it this formula here, let me repeat it briefly. When we got the formula for this rod, this is a formula of this rod, a multiplied by L squared divided by 3. This was the formula relative to the axis y, z, and the polar moment 0. Because this reference system was the reference point of the system of coordinates was associated to the end of this one rod. So when we associate this not with the center of the mass of this mechanical rod, when we associate the center of the coordinate system with the end of the mechanical rod, we can find the formula of the moment of inertia equal to a multiplied by L squared divided by 3. This contains together for the rod only the on and the transfer moments of the inertia due to the Huygens-Steiner theorem. This all two are inhered here. The sum of the on the transfer moment inertia of the mass of rod 1 and the homogeneous disk is so. This is a total for the rod. This is total for the total moment of inertia relative to reference point 0 for the is a point of the suspension point. This is total moment of inertia of the homogeneous disk. The total moment of inertia of homogeneous disk consists of two summands. The first summand is the own moment of inertia of the consists of own moment of inertia of the homogeneous disk, and it consists of the transfer moment of inertia of the homogeneous disk. So we have together having the own moment of inertia, this radius of disk assigned L divided by 4 squared divided by 2. For disk we got that the moment of inertia for the disk we have mr divided by 2 we had before got, and this is transfer moment of inertia m divided by 2 multiplied by 5 divided by 4 multiplied by L and squared, L squared. This is total moment of inertia of the disk. And we have the transfer moment of inertia squared. Why 5 divided by 4? Because the distance between the suspension point to the center of the disk, center of the mass, is equal to the length and to the radius. Radius is 1/4 part of the length. So the total distance from 0 to c equal to 5 of 4th part of the length assigned. So, and but I just watched the mistake here. One mistake here is what we have to have here only the mass, no divided by 2, just a mass, multiplied by this different one, and the factor on the squared in the brackets. So this is size squared multiplied by the mass of the disk of mass. Yeah, okay. And moment of inertia total, and we will have this one, the right side of this total moment of inertia consisting of the own and transfer moment of inertia of the disk. And when we consider this all two as the I1, the moment of inertia together having this definite one formula of the rod suspended by the end, and this consists of the own and transferring moment of inertia and the moment of inertia transferring for the disk, consisting of the own moment of inertia disk and the transfer moment of inertia with the correct here have to be just only the m not divided by 2, just a mass of the disk multiplied by the definite one, bracket squared, brackets is the distance between the suspension point and the center of the mass of the disk squared. And after that we can have that the total moment of inertia of this pendulum relative to the point of the suspension is 100, and transform as well. We can multiply this by 2 denominators. We will have 96, and we next we have to multiply this as denominator by 32. The same we have numerator multiplied by 32, and this we have to multiply by 3 because this is factors of the common denominator 96, and we will have 185 multiplied by m by L. So this is dependence of the total moment of inertia relative to the suspension point for this pendulum, independence on the length as a variable and on the mass. If you will know the definite mass and definite length, we will have the moment of the inertia as a definite magnitude of the masses multiplied in units of mass multiplied by the units squared units of this size. Questions and comments. Moments of inertia of the mass of mechanical system and the elements which are characteristics of the distribution of masses in them and scalar characteristics of the inertia in rotational motion. Moments of inertia characterizes the inertial characteristics in the dynamics and in the issues of dynamics when we consider the rotational motion of the mechanical bodies and elements of the mechanical system, or in the equations with the oscillating of the elements mechanical system, if this is oscillating of the angular parameters of the motion of the elements of the mechanical system. 1042 moments of inertia of the mass relative to the coordinate axis and relative to the pole of rotation. The polar moment of inertia, the radius of inertia relative to axis and the polar radius of inertia. The radius of inertia equal, any radius of inertia is equal to the square root of the moment of inertia appropriate divided by the mass of the mechanical body. So this will be the moment, the radius of the inertia, and if we under square root when finding the radius of inertia have the polar moment of inertia, this will be the result of the polar radius of the inertia. If the actual accelerated definite axis moment of inertia, we will have under square root divided by the mass, we will have the actual radius of the inertia. So the radius is as well characteristics of the inertia of the distribution of the material of the mechanical body, and the distribution impacts onto the patterns and the laws of the motion, angular motion in the shores of the dynamics. 10-4-3 axial and polar modes of inertia of a mechanical system consisting of the rigidly connected elements. For the rigidly connected elements, we can find the polar modes of inertia of mechanical system as a total of the products. Total of the products for each rigidly connected element. We have to have the mass and multiplied by the squared distance from the definite one element to the, I mean, if it is the located concentrated element, maybe concentrated mass, or maybe the segment of the volume of the continuous mechanical body, we have to find the distance between the axis, or between the polar of the rotation, of assuming rotation of this segment, and the distance from this segment to the polar or to the axis, and find this distance or squared as not just a distance, but we can use Pythagorean theorem as in the Cartesian coordinate systems. The distances usually we can find having the components of the distances. But if we need to find any distance in the Cartesian coordinate system, we usually do the finding the square root of total of squared of two components or three components of the that is coordinates of the location relative to the assigned the reference point. But in the finding of the moments of inertia, we don't need to find the square root, because in the formulas for moments of inertia there are directly the squared distances. So we just only to find two squared coordinates or three squared coordinates of the distance between the reference point, or between the center of the mass, if the reference point coincides with the center of the mass, and with the definite one, the mass, if we find the moments of inertia not related to the center of the mass. 10-4-3 axial and polar moments of inertia of the mechanical system consisting of rigidly connected, as we told about that, tell about that. 10-4 axial moment of inertia of mass of the rod related to perpendicular axis passing through the end perpendicular to this axis of the rod, polar moment of inertia of the rod related to the origin of coordinates of the system of axis. If we associate the reference point of the coordinate system with the end of the rod, the polar moments of the inertia of the rod, as well as the axial moments of inertia of the rod, I mean the relative axis not associated with the rod itself, not passing by the rod. The perpendicular axis, the moment of inertia equal to the mass of the rod multiplied by the squared size, the length of the rod divided by 3, if we have the reference point associated to the end of the rod. If the reference point associated to the mass center of the rod, the moment of inertia, I mean polar moment inertia or axial moments of the inertia are equal to the mass multiplied by the length of the rod square divided by 12. This is only not for the moments of inertia relative to the associated with the rod itself, passing by the axis of the rod. If we consider the axis of the rod, then considering the small size of the rod in the transverse direction relative to the size of the rod by its length, then we neglect the moment of inertia relative to the axis passing by the length of the rod. 10, 4, 5 dependence of dimensions of a rectangular plate of the actual moments of inertia of mass relative to the coordinate axis passing along the sides of this plate and relative to the axis passing through one of the vertices of the rectangular shape perpendicular to the plane or of the plate. So if we have the plate of small thickness and definite sizes like length and width, so the moments of inertia depends on the axis assigned to find the moment of the inertia. So if it is the axis coincides with the definite one side of the plate, then the moments of inertia equal to, the axial moments of inertia equal to the product of the mass of this plate by the size of the plate in the direction perpendicular to the axis to which we consider the moment of inertia and divided by 3. And we multiply, let me just remind that we have to multiply by the size, squared size of the plate in the direction perpendicular to the considered axis, finding the moment of the inertia. And if we consider the moment of inertia relative to one of the vertices, we consider the moment of inertia of the plate. Then we have to find it as the mass of this plate multiplied in the brackets. We have total of squared two sizes of this plate with not the thickness only, and this all divided by 3. This will be moment of inertia of the plate. 10 for 6 moments of inertia of the mass of flat solid homogeneous disk relative to the perpendicular axis passing through the center of the disk in the plane, as well as the moment of inertia of the disk mass relative to the axis passing through the center of the disk perpendicular to the plane, which is equal to the polar moment inertia of the disk. So we have the formulas finding the moments of inertia of the disk here. It is the moments of inertia mass of homogeneous disk is relative to the axis ordinate and applicata. We have mass of disk multiplied by r squared divided by 4, and relative the longitudinal axis x, not longitudinal but the transverse, perpendicular to the plane y0 z, the axis x, and the moment of inertia relative this axis x equal to the mass multiplied by radius squared divided by 2. This is twice greater magnitude of the inertia when rotating the disk around the axis x than if we rotate the disk around the axis y and z. Moments of inertia of the mass over in the polar and actual moments corresponding to the difference between these moments of inertia of flat solid homogeneous disks, external and internal, the geometric difference of which is the ring. For the ring, moments of inertia is indicated here. We assume that the ring is a segment taken over the disk when the definite disk we from the order size subtracted with the definite characteristics of inertia of the disk. We subtract the disk of the inner side with definite characteristics of inertia of the disk of the inner side, and the rest part is the ring. But for the thin ring, we have the moments of inertia as r squared relative to the abscissa axis, and the y and m r squared divided by 2 relative another two axes perpendicular to the ring or to the disks. Moment of inertia of the mass of round solid cylinder relative to the cylinder axis, the same as for the disk, relative to the axis perpendicular to the plane of the location of the disk. Relative to, and the moments of inertia of the mass of round solid cylinder relative to the axis passing through the center and in the plane of the base of the cylinder. This is about the same as for the rod we have, and relative to the axis passing through the center of gravity of the cylinder perpendicular to the cylinder axis. The cylinder we can find two moments of inertia if we associate the reference point with the center mass cylinder as this ml squared divided by 12. This is moments of inertia abscissa and ordinate axis. And if we associate with the base of the cylinder, this is ml squared divided by 3. So 4 times more than if we associate with the center of this mass of the cylinder. 10 moments inertia of the mass of the ball related to the coordinate axis passing through the center of the ball, and the polar moment of inertia of the mass of the ball relative to its center. Moments of inertia of the ball relative to the center of the ball. The polar moment of inertia, this is 2 divided by 5 multiplied by m by r squared. This is 3 divided by 5. So polar moment of inertia is for the solid ball is greater than the axial moments of the inertia. 1.5 times. The polar moment of inertia is greater for the ball. And 10, theorem of Huygens Steiner about the moment of inertia of the mass of the mechanical system consists of rigidly connected elements equal to the sum of own moments of inertia of each of the elements in the coordinate system associated with the center of the gravity of the element. This is, this own moments of the inertia of each one associated with the axis passing by the center of the gravity, center of the mass of the definite one element. And for actual moments of inertia of the mass parallel to the axis relative to which the moment of inertia of the mechanical system is sought. And we have another one system of coordinate, arbitrary system, which not coincides with the system passing axis which of pass through the center of the mass of this element. And the transferring moment of inertia, each of which is equal to the product of the mass of the element by the square of the distance from the center of gravity of the axis to the axis of with respect to which the moment of inertia of the mechanical system is sought, or by the square of the distance of the point with respect to which it is determined polar moment of inertia of the system. So when we find the moment of inertia of any element mechanical system or discrete body or solid body, the moments of inertia of these elements are we have to assign the axis and the reference point of finding of the moments of the inertia. And if the axis and the reference point coincide with the center mass of definite one mechanical body, then we will have the own moments of the inertia. If the coordinate system is outside the center of the mass of the mechanical body, we will have two moments of the inertia, the own moment of inertia and the transfer moment of inertia, considering the distance between the assigned reference point of the mechanical of the coordinate system and the center of the mass of the mechanical body. And the transfer moment of inertia and the own moment of inertia together give us the total moment of the inertia relative to the assigned coordinate system. Thank you.